Sorry for a slight delay. Give me one more minute. Please give me one more minute just to start our lecture. Okay, you should see my screen now. Let me just make the recording active. Okay. Okay, let's begin then. So welcome everybody once again with a slight delay during our last lecture this year. And we continue, we take over from the point we stopped or we paused last time. So the thermal management. Thermal management, the last element that we were analyzing was the advantage of forced convection, so of using together with the heat sinks forced airflow, and of course the larger the airflow, the better. But naturally, what we shall remember is that it's not all that shines is gold, which means that of course the adding of forced airflow reduces the thermal resistance of the whole setup of the radiator. Yet the dependence isn't linear, which means that the increase of convection in the from 0 to some value gives higher gain in the reduction of the thermal resistance. Then the curve flattens, which means that we may have a hurricane near our board, and it might not solve our problems, and we might need to simply increase the area of the wings in our heat sinks. In case of the thermal conductivity, that might be interesting as well for you, because what materials what's the reason of? Okay, we have a question. What do you mean by this? Leave early. If you leave earlier, there will be still the recording available. Because I'm recording the lecture, so if there is anybody leaving, so there will be a recording available, if not today, then tomorrow on the webpage, so you can then finish the lecture from the offline recording. Okay, so this chart shows or proves why the aluminium is the major element or the major material used for the heat sinks itself. So this is the thermal conductivity of the aluminium, which is 266 watt per meter per Kelvin. Of course, it's worse than the copper and silver, but the prices of the copper are much higher. Still, of course, the silver, forget about it. It's absolutely not useful for any heatsink applications. The copper, sometimes we are using, frankly. Sometimes we are using for special cases where we really need the thermal conductivity to be better, because we have a gain from aluminium to copper. The gain is about 40% higher conductivity. Of course, the price of aluminium, the weight of the aluminium, the workability of the aluminium, these are negative features. Positive features for the aluminium and negative in the case of the use of copper. But still, this 40% gain in the conductivity is tempting. So sometimes the copper is used for this purpose. The steel, the use of steel for the heat sinks themselves isn't the best idea, actually, because we lose quite a lot. We lose a lot, not quite. We lose really a lot. because it's about 1/3, less than 1/3 of the conductivity of aluminum. Of course, the price of the steel is lower. Of course, steel is mechanically better because it's sturdier material, it's stronger than aluminum. And it's much cheaper. Yet this high difference, very significant difference in the comparing to the aluminium, and much higher, worse workability. In fact, because we need better tools to do this. So the material is cheaper, but from the construction point of view, it's not really better. And for this reason, the steel is used very seldom. For those reasons, the steel is used very seldom, or seldom, maybe not very seldom, but much more often we're using copper instead of aluminum. Still, the first choice for the heat sinks is copper. Second place in the electronics is copper, and then a large gap, and steel comes there as not fourth, but as on the third place in case of conductivity and the heat sinks. Also, for the comparison, the water and dryer conductivity, especially the dryer, is interesting here because it's extremely low. It's just 0.04, which is nothing. And what's the problem? Why am I stressing it? The reason for this is that we need, of course, to when we have a component. There was the where is this slide? Here it is. So when there is a component and there is a heat sink, the surfaces accidentally I've drawn it this way. The surfaces are not flat, of course, and they are far from being flat normally. So the surface here is of a PCB, but try to imagine here a heat sink. And here is the component. Case. So they are not completely flat, which means that if we stick them together, then they join on a very, so the connection is thermal connection is on a very limited surface, and besides these areas, very rare areas of connections, and sometimes just 3 points. We have an empty space here. So we have an empty space here and here. This empty space is filled with air if we don't apply anything special. And the air is very bad conductor. For this reason, we have to add some conducting. Usually we are adding some conducting paste. Of course, we don't add water here, but we are adding some conducting paste, and those pastes are those ones. So here under the name of Arctic Alumina, Arctic Silver 3, but basically this is the range for various thermal pastes. You can buy those thermal pastes in any electronic workshop. Of course, they are far from aluminum. Even far from steel, because usually they have this coefficient of thermal conductivity very weak. But of course, we need only a thin layer. On the other side, don't forget about using them only on thin layers. Never use them on layers having 1 millimeter, 2, 5, or 10, because they are much weaker conductors, thermal conductors, than the aluminum, copper, and even steel. So that's important. So we have to avoid the problem with dryer between the heat sinks, and use the some paste, thermal conductive paste instead. And then we come to a very interesting element which is quite often used in the electronic, in small electronic devices. Quite often used when we need to stabilize the temperature. This is a heat pump. In general, this is a small heat pump. The heat pump heat pump that is capable of pumping the heat in 2 directions. That's interesting. Because with the standard heatsink, we can only pump the heat out of our device. We talked about the models, thermal models, and there was only the one direction, I would say, for the heat. With the use of the Peltier element, we can pump the heat in 2 directions. It's a very interesting element. So the Peltier element, depending on the current that we apply to it, we have because we can modify the current flow, and with the modify the current flow, the heat is being transported in 2 directions. So the direction of the heat transfer may be modified, so it may be left to right or right to left, depending on the current applied. So how is it built? How is it constructed? This magic element. So there is a bismuth telluride, which is a semiconductor. It is sandwiched between 2 conductors, usually a copper. So here is a conductor, and here we have this semiconductor, this bismuth telluride element. The semiconductor is doped with the N-type, so with electrons, but they are used. They are used p-doped and n-doped, as you will see in a moment. With the n-doped semiconductor, the electrons move towards the positive end of the battery. And when the voltage is applied, the heat is transported in the direction of the current flow. So when there is a current flow, the heat is transported in the same direction, or like here. So for the n-doped source, we have the electron flow here and the heat flow here as well for the n-dope. Then if we make a p-dope, then we have the direction being in the reverse, being reversed. So the heat flow is pumped from, take a look, here we have a plus and minus, which so that's the polarization of the DC source, and the heat flow is from minus to plus in the same direction. Here from plus to minus as well, there is plus top, minus bottom, but the heat flow in the p-doped part is from plus to minus, from this connector to this conductor to this conductor. And then if we then construct such a device like a combination of alternating thermal electric devices, so those doped semiconductors N and P, but connected in such a way, in such an alternating way, then it turns out then we can, changing the polarization here of plus and minus, so we can have a configuration where the heat is absorbed here and released here with this polarization. But then if we modify the polarization, so change the plus to minus and minus to plus, then the direction of the heat flow will change. So we will have a direction going so that the heat will be absorbed on the top part and released at the bottom part. Fantastic, isn't it? Yes, I must admit it is very excellent and very, very nice device. So this Peltier element. With this element, we can really modify the heat flow just by changing the electric current. As well, those devices operate. We can modify the operation, so we can modify the stream, the width of this heat flow, so we can modify how much heat is being transferred just by changing the voltage and of course the current, so the power delivered to the Peltier component. So we can really, in an analog way, either stop any heat flow or reduce it very much, reduce it very close to zero by applying no voltage to the pins, to those connectors. Or then we can change the heat flow upwards or downwards and regulate the flow itself by changing the current and changing the voltage. That's very interesting. That's very nice. That's a very nice component. Yet again, not all that shines is gold, and of course, this thermoelectric, this Peltier component. It's not perfect. It's not completely perfect and completely flawless. What's the major problem? The major problem is that the element itself, works, so its performance, the capability of transferring heat, its efficiency, that's the word I was looking, its efficiency depends greatly on the temperature across the Peltier component. And the best we can do when the temperature between hot and cold side, as we call it, is zero. What does it mean? It means that the most effectively the transport is going on when the temperature here, the temperature the absorbed side and the temperature of the release side, when they are equal. So TA and TR when they are equal. Then the heat transfer, the efficiency of the heat transfer is the highest. Yet when the temperature starts to rise, so when we have a 10 degrees, for example, difference, then instead of 40 watts at certain applied electric power, because it's a heat transfer, yet at the constant electricity delivered and the constant electric power being delivered. So here at the constant electric power, we have already a 10 degrees difference. The heat transfer capability of certain Peltier module reduced from 40 watts to 34, which is about more than 10% less, about 15% less. Then if we consider 30 some degrees, 36, 37 degrees temperature difference, then the efficiency drops by 50%. So here the efficiency isn't 100%, of course, because the Peltier never has 100% efficiency of power conversion from electric to heat transfer. But here, even this limited efficiency is reduced by here 50%. It's by 2. Of course, it's the efficiency by 2. And here everything goes even worse. Here the efficiency is by 4 and so on. You might ask, yeah, but what's the problem? Let's work here. Let's work at 0 degrees temperature difference, and then the efficiency will be maximal. Of course, we should do this. But the problem is that if we take some heat from the absorbed side, from the cold side, then the temperature here will start to fall because we take the heat. On the other side, if we deliver the heat to this part, to this conductive conductors at the release side, then those conductors will first absorb the heat because of the certain thermal capacitance. But then they will start, the temperature TR will start to rise. And therefore, even if at the beginning in the equilibrium state TR was equal to TA, then soon after we start pumping heat, the TR and TA the difference will start to increase, which does mean that the efficiency of the whole heat transfer will start to decrease. And what is worse, it will start to decrease. But take a look. here we were able to transfer 40 watts. So let's say that the efficiency the efficiency was very high, and so it was about 90% Let's say that it was that high. It's possible at zero degrees, at zero temperature difference, but that would mean that we were dissipating about 4 watts in the Peltier itself. Here on the other side, which isn't negligible, by the way, but let's neglect it at this moment, because here at this point, the amount of power dissipated in the Peltier element itself jumps from 4 watt to 24 watt. Take a look. We have here a positive, unfortunately, a positive loop, because the more heat we want to transfer, the more energy is dissipated here inside the Peltier, heating up the Peltier, and the more the Peltier heats up, the worse efficiency it does have, and the more energy is lost in the Peltier elements themselves. So it's a positive feedback, and this is the major disadvantage of the Peltier element. So at one side is the element, the only one we have, in fact, to pump heat in 2 directions just by changing the polarity of the electric signal. On the other side, it has the disadvantage of possibly positive feedback in case of the power loss and the temperature rise and the efficiency reduction in the Peltier element itself. For this reason, although we have very nice Peltier elements delivering the heat up and down, we really must not forget about placing here a very good heatsink. So the Peltier element is nice, but we must have here a very good heatsink. So the heatsink, of course, the role of the heatsink is the reduction of the thermal resistance of the hot side of the Peltier component, of the Peltier element, and dissipating as much heat as possible to the ambient or to the destination. So don't forget about it. So the Peltier component is very nice, but unfortunately it has this very unpleasant flaw. Another unpleasant flaw is placing two thermoelectric components onto each other. So you might think, okay, let's, instead of one component, let's make a stack. Let's pile them up together and make let's stack it up and increase the capability and increase the capability of the cooling or of the heat transfer. Cooling, it may be heating up. It's not about the cooling. It may be about keeping temperature constant, for example. Theoretically, the number of stages increases the coefficient of performance for a given cold side temperature. So theoretically, it might work, but from my perspective, I wouldn't recommend it in general. I wouldn't recommend these multi-stage modules because they have to be driven in a more complex way, and of course theoretically they give some advantage, like shown here, but in practice that's not really working. So of course this element, so it's not pumping out the heat itself from the bottom one. We still need a very good heatsink here to be connected. So this additional component, this additional stack of Peltier elements, it's not solving the problems of proper heat sinking at the hot side. So I would say don't try it itself. I would say don't try it. So you can try, of course, but I'm very reticent about very skeptical about the outcome you receive with piling up 2 or 3 or even more thermal Peltier component. Normal configuration of the Peltier component you can see here at the slide. So typically we have the heat source, and then we have a very good heat sink, even with the fan, circulating here. So with the forced airflow, and then of course there might be a question from your side. So if we need the heatsink and even a fan, so what's the reason of using the TE module, the Peltier module or TE module, thermoelectric module, whatever the name? Yeah, and then once again, the reason for this, the TE module, the major advantage of TE module compared to the standard use of the heatsink and the forced airflow element, is that with TE module we can of course direct the heat from the heat source to the ambient, but by changing the polarity, we can reverse the heat flow, which means that with the TE element or the Peltier element is the very standard component if we want to keep the temperature stable of some component, of some element. So for example, if we want just to dissipate the heat because our power amplifier or the DC-DC converter is heating up too much, or some linear regulator is heating up too much, then it's enough to apply a heatsink and force the airflow if necessary. But if we want to stabilize the temperature, because for example we have a laser source and we want the laser source to be stable, and other situations we need a very stable clocking system, and we need to stabilize the chip generating the clock, then in those reasons, in those situations, we are using TE element. Of course, we are using the second application where the TE elements, TE modules are used, is where we need to dissipate the heat or to pump out the heat in a very fast way. Sorry, not this. I meant the second situation is when, a very important one as well, is when we want to get with the temperature of the element below the ambient. Below the ambient, again, going back to our model. Where is our model? Fantastic. Here is the model. Take a look here. Normally we have so let's say there is a heat source, and let's say that we have the thermal resistances somewhere, and then we have the ambient. Even if we reduce the temperatures down to zero, the resistance down to zero, in the super perfect case, which never happens, then the temperature here, the temperature of the board, let's say, or of the component, will never be below the temperature of the ambient, because with the resistances being zero, theoretical of course, the TB would be TA. So the Peltier element we are using in those situations where we need TB to be lower than TA. We are not able to do this with the classic static, I would say, or passive, not static, but passive cooling elements, only with phase change. like we have in the fridges. But this requires complicated mechanics. This phase change cooling. Normal electronic devices, we don't have as much space. So if we need the situations where TB is lower than TA, we really must use a Peltier component. So those two situations basically. What about the pricing and the availability of the Peltier element? The Peltier elements in real life, they are very easy to be obtained, very easy to be found. Again, in any electronic workshop, the standard, so they are available usually as squares. So we have usually the size of the it's usually a square. Squared area. The sizes you can find, they vary. I would say the basic one is about 25 by 25 millimeters. That's something you can expect as the common element used in electronics. Also, you can find something like 20 by 20 or 30 by 30, and of course the sizes go in both directions. Yet this is quite common size, so about 20 by 20 to 25 by 25. Then how much heat can it pump out? Those 25 by 25, the range is about 10 watts. That's about the amount of energy you can try to pump out and pump in, because of course it works in both directions. Of course, if this is reduced by the efficiency, so this the power, the possible heating pumping power is reduced. Again, the voltages you're applying to give you the idea as well. For this size, so 25 by 25, it's about the voltages expected here by the Peltier itself are about in the 3 to 5 volt range, and the currents that you must be ready to deliver are about 2 amps. So it's 2-3 amps. Actually, this range, so it's definitely not in millivolts range. It's actually much higher. Still, if you don't need 10 watt, if you need less, then you can reduce the voltage here from 3 volts down to 1, and then the current will be lower, because the Peltier is seen as a resistor electrically. So it has a resistance of ohm, 2 ohms, 3 ohms, something like this. So that's these are the values that you can expect from the modules available on the market, available for use in this configuration. So again, two major usage of TE modules for changing the direction of heat pumping, of heat transfer, and for stabilizing below the ambient temperature at the temperatures below the ambient. For those two in those two situations, we're using it in practice. How we supply it, we are using, if you still didn't get it from the previous slide, we need a DC power supply. We need a DC power supply. A bit important thing, again, from practical point of view, is that the DC needs to be of a decent quality. What I mean by this, yeah, if we draw a schematic, theoretically, let's say that this is the Peltier element. So we have some power supply here. The standard schematic, this cursor that we are using, is to use the MOSFET. Today we are using almost only MOSFET. Is to use a MOSFET for switching on and off the current flow to the Peltier, switch on the heating. But of course, this first of all, so this very simple circuit has one disadvantage, serious one, is that it's just either heating or cooling, because it's not changing the polarization. Here we are just keeping the same polarization. Second problem of this circuit is that it's about full power or no power. It's switching 100% cooling and or on switching off the cooling, or 100% heating, full power heating, and then power off completely. So that's the disadvantage of the circuit. Therefore, if you want to have linear regulation, then the simplest application would be to use, instead of a MOSFET, is to use a circuit with NPN, and then to drive the NPN, so to polarize it then would be nice, and to drive it then through from some source, voltage source here. Then this would, of course, the disadvantage of the advantage is that we have a linear current flow, because we can regulate through the applied voltage here. We can regulate the current flowing and the power of the Peltier component. Yet the difference of this, the problem with this method, with the NPN transistor, is that a lot of power will be, because the transistor here works in the active mode, so a lot of power will be dissipated on the transistor itself. So that's the disadvantage. So either you have a choice in case of Peltier control, either you have to drive it with on-off mode, or you have to prepare a good transistor for power dissipation, because a lot of power will be dissipated in the transistor in this configuration. Here, in this configuration for MOSFET, good MOSFET transistor, the transistor will be very cool, much cooler. So the overall efficiency of this circuit is, of course, much better than here. Yet here the regulation is better. Here the regulation is a bit problematic. And the second matter, because this circuit is for linear regulation. If you want to change the polarity, then unfortunately you have to use. Will not be drawing it here because it's with this with a mouse. Drawing with a mouse isn't the best idea. Anyway, we have we must use an H bridge. So instead of those elements here, and here, there are four switches. We have to, of course, use MOSFETs, and here are P-tape MOSFETs, two P-tape MOSFETs. Here are two N-tape MOSFETs at the bottom, and then with this H bridge, classical H bridge, we are either switching those two transistors or those two transistors on and the other one off, causing the current to flow either in this direction or the current to flow in this direction. So this is the H bridge, is the standard method of controlling DC motors, for example, because then we can change the rotation direction of the DC motor. But as well, we are using it for changing the polarity and changing the heat flow direction for the TE elements. So these are three major circuits for driving the Peltier. One small practical remark, very small one. We don't have time to make it to explain it in greater details, but this circuit, if you want to use it here in this place with the arrow, there should be much better results are received when you put a strong coil here. So add some inductance. This inductance increases the efficiency, or maybe in other words, reduces the efficiency problems of this Peltier element during switching, because this Peltier element doesn't like steep switching, which would be the case for in this configuration. And to avoid problems in these configurations, a strong coil, which means because there is a lot of current required, so there has to be a strong coil, 10 microhenries, 22 microhenries, something like this is good enough. Yet for 1 or 2 amps should be added here between the power supply source and the Peltier component, and then the results, the efficiency of this circuit would be higher than without this component. So small practical remark. Yeah, so here is the nothing very special. The next part of our lecture is about a few words about the fans. It's about the forced airflow, because as well here we have a few options, from practical side. But as we have a break, so let's stop for 15 minutes, and we'll get back to this cooling system, to the next elements of the cooling system, to fans, right after the break. So let's now have a break, and we'll get back to this after the break. In case of the next element of the cooling system, which is a fan, we have indeed, from the perspective of a designer, we have a couple of choices. So we can use the fans being DC supplied, the fans of AC supply tape, and the brushless tape. Brushless tape motors are available as well. In case of bearings, we have an option of a sleeve bearing, ball bearing, and vapor bearing fans. There are slightly differences between them. So the vapor bearing, vapor is the vapor bearing special tape. It's for reducing wear. It's eliminating wobbling and so on. So it's very nice. Comparing to the standard bearing, but the bearings may be less important, let's say, from practical point of view. They are, so there is of course the sleeve bearing and the standard ball bearing, of course, is stronger than the sleeve one. Vapor seems the best one. So Vapor is very much the magnetic bearing here. So that's they are slightly better mechanically, but frankly, from the practical point of view, we are much more interested in this. So if the fans are AC motors, DC motors, or brushless motors. In case of AC motors, we are interested in electronics in rather smaller fans. We are not interested in very powerful fans, which means that we are using single-phase motors, single-phase AC motors. It's three-phase AC motors are very, very seldom to be found. Still, the AC motors are not the first choice in the electronics. So they are sometimes we're using these single-phase AC motors for example, for cabinets. If you want to keep to pump the heat out of some cabinet or some shelf with electronics, then we turn towards usually single-phase AC motors. The good thing about the AC motor is their simple construction, simple and reliable construction, let's say. That's the advantage of the AC motors, because we have no mechanical contacts here. Everything is magnetic, which means that the AC motors can work a long time mechanically. Yet the problem is that we have very limited possibilities of regulating the speed of these motors, because the speed of the AC motor is tied to the frequency of the AC signal. That's disadvantage number one of AC motors from practical side, which means that if you want to regulate, if you need to regulate the airflow in your design, to do this with AC motor, you need to have special frequency converter, which costs quite a lot of money quite often, because it's actually AC converter. So for a few amps, or for tens of or hundreds of watts, it's not for free. So you have to pay extra for it, and that's the disadvantage, which is sometimes a deal breaker. So the AC motor is good if you want to keep it at constant RPM and at a constant heat flow. Second disadvantage of the AC motor, smaller one but still important, is that you need a special capacitor, which is usually not included inside, but that you need a special startup capacitor, because the AC single phase AC motors need those capacitors, or require those capacitors. The capacitors, the problem is that they have to be quite large, because we talk here depending on the power of the motor, but for tens of watts, the capacitors are going closer to microfarad even, although for smaller motors they may be lower. The values may be a fraction of a microfarad, but still a couple of hundreds of nanofarads for 400 AC volts, because these are the voltage rating, means that the capacitors are usually significant. They have significant size. Significant means that the capacitor is usually a tube with a few centimeters. So it's usually a tube with 2 wires. That's the capacitor if you haven't seen it. And if you have a 15-inch screen, then this capacitor should be 1:1 in scale on your computer. So that's significant. So that's quite large, and that's the second disadvantage of this motor. Those two disadvantages are missing here with the DC motors. So DC motors, they are mechanically not as good, as sturdy as the AC motors, because there have to be internally there are connectors from wires to windings on the rotor, because the windings are rotating here. But that's the disadvantage. But the advantages of the DC motors is that you can very easily regulate the torque of the motor by applying various voltages. As well, changing you don't need any startup capacitor here, because the direction of rotation depends on the polarity of the voltage. And that's the advantage of the DC motor compared to the AC motor. In practice, as well, for this reason, the DC motors are used in very wide. They have very wide applications across the electronics. You can very easily, of course, because changing the torque means that you are changing as well the RPM, the rotation, or the airflow obtained from such a DC motor. So those DC motors today are very cheap, and they are existing in various sizes. So starting from, in practical applications, you can find the DC motors from a few centimeters by a few centimeters. So these sizes, so 2 by 2 centimeters, are, for example, obtainable. As well, larger sizes available as well. Lower, not really, because still mechanically they are required some magnets, some windings, so they are not extremely miniature. If you want something smaller, you have to use Peltier and passive cooling. And the last one, not mentioned here, the last type of fans, which is becoming more and more common today, is the brushless tape. The brushless motors. So 2 types of motors are available today. So it's BLDC and PMSM motors. It's actually motors with permanent magnet. They are different in the mechanical construction internally, but the basic rule is, or the simple thing to remember about those 2 brushless tape motors, is that they require way more expensive control, but they are they deliver much higher efficiency. And what is meant by why? What's the reason behind those features? The BLDC and PMSM, so actually the brushless tape motors, they have construction very similar to the AC three-phase, but not single-phase, but three-phase AC motors. Yet they are designed to be DC supplied. So it's actually sort of a combination of a DC supply with 3 windings and with the brushless construction of the AC motors. So the no brushes means less noise, means no moving elements, no moving contacts. That thus far higher reliability of such motors, thus far higher lower noise, for example, better torque and so on. The problem is with the brushless tape is that the full control is given to the microcontroller. So there is required an MCU, dedicated one, usually just to drive the brushless motor. Today it's not a problem because today we can find small microcontrollers capable of especially designed for the brushless motors, especially delivered for the integration with brushless motors and for the control of brushless torque and brushless rotation and so on, because a couple of things microcontroller must measure. So the overall construction is more complex, yet today the brushless motors give a very high reliability if you are able to cope with the electronics, but they have very high reliability and excellent parameters at lower weight and even I would say lower price. Overall cost is even lower today. So today the brushless is, you can find, for example, in various washing machines from the large side, but as well the brushless motors can be found in any drones, because today the drones are the brushless are very easy and efficient in controlling in changing the rotation speed. It's very easy as well to change the direction and so on. Therefore the brushless are very popular, for example, in such applications. Okay, that would be it about the thermal system. Now a bit of a slideshow about the possibility of cases of the electronic devices, because when you build something, preparing your device, preparing a case for a device might be kind of an issue. We mentioned some time ago, maybe before we go further, about the power supply. So when we were here, that during the design of your electronics, the power supply becomes a kind of a false friend, an element which seems to be very easy and negligible, but the element that must not be negligible, must not be neglected, and must be really taken care of. With cases, it's not as critical, yet if you want to build something, and if you want to build something that will be used by some people, some non-professionals, or that it will be used as a standalone device, then it turns out that the proper design of the overall of the outer case, including the required characteristics of the object, requiring the proper thermal management, the proper EMI, so electromagnetic interference, the placement of antennas, and as well the human-machine interface, so like displays, like buttons, like switches. So if we start to consider all those factors, then it turns out that the case shouldn't be left, the choice of the case of the device shouldn't be left to the end when everything is already done, the PCB is running and everything is working as expected. But it turns out that the choice of case a case of our device should be done at a quite an early stage of the project, at least a preliminary choice of the case. Because, why is that so? Because we may have a situation, or we may have a design where the space is not a problem. Then we can use, for example, 19-inch, so-called 19-inch system. The 19-inch system is a system of cases where with a lot of space. So for the situations where we need to integrate a lot of electronics with displays, with fans, with some electromechanic parts even. This 19-inch system bases on a shell, on a rack. Where is the rack? Bases on cabinets, maybe not rack. It bases on cabinets. So there is a whole huge, there are many suppliers in the world delivering various sizes of the cabinets. The size here go into, it can be a meter, 1 meter, it can be 2 meters even high. The width of this is more standardized of this cabinet. It is standardized to accommodate the shelves. The shelves are as well standardized here with T size, inch based T size, the T or HP, because again different marking is found. They are norms international. Take a look even describing this system. So we have 5 millimeters, 508 millimeters here as one T unit, and the basic width of the shelves, like this one or this one or this one. Here is a cabinet for the shelf, small one. But for example, this shelf, or here is a computer integrated inside the shelf. So the size here is 84T. TE or HP or T, whatever, which is 84 times 5 millimeters, 5.08, which means that it's the overall the width is about slightly more than 420 millimeters. This is the standard size. Take a look. So quite a large case. As mentioned, this can be placed usually in some cabinets like this one, where we can place usually a lot of shelves. How many shelves? It depends. Depends about the second dimension. The second dimension is given in U. In U units, the U itself is again a very strange value from metric system point of view. It's 44.45 millimeter. It's 1 U. The shelves are existing in different size. So here is the shelf with one U. We can place some electronics here, some ventilators, for example, or some mechanical element, whatever we need. Here is an example of the racks or shelves with 3U. This shelf was, here it is. Where is it? This one is, for example, 6U, so 3U here and 3U here. So altogether, it's even 9U. Sorry, it's even larger. But they are 6U, they are 9U, and in case of those cabinets, they are available again to accommodate 20U, 40U. So those sizes are accepted by those cabinets. What's also interesting is this size. It's not really standardized this time. So the depth of the shelves, the depth, there are a few sizes which are, let's say, common, but still it's not, the depth itself is not really standard, but it can be as high as, again, about 400 millimeters, or even slightly larger, the elements you can buy, because all the system itself is composed of blocks. It's like a Lego technique, yet for professionals, which means that you're buying or like IKEA again, that you buy the elements of the whole system on Mauser, Farnell, for example, or some other TME shop. In the shops, you're buying the self-made elements that you are just assembling together using a screwdriver, and then in order to place your electronics inside. So this is one option we have. But that's the option we have for large electronics, for large boards, or where there is no space limitations. Of course, the disadvantage of this 19-inch system is that it's it's quite spacious, and expensive as well. Which means that if you want to build something smaller, then this system is no go. So of course, it's absolutely no choice. Then we are for smaller elements, for single PCB, for example, designs. Then we have a wide choice of universal cases. The cases which are available in different shapes and sizes, as well composed of different materials, because as you can see here in the slide, these are plastic cases, various colors, but mainly black. Yeah, like first, fourth T. All colors available, but if the colors are black. So we have plenty of cases from plastic available. There are as well the cases from steel, because steel is cheaper. Therefore, on the market there is a choice of cases of painted steel, of rectangular shape, because usually the steel cases are are rectangular shaped. If you want some more fancy cases, like take a look, here is a very fancy case. Here is a fancy case. These are usually from plastic. There is also a large family of aluminum cases, but from aluminum profiles, very common tapes, or plenty families in the market from the profiles, which are then have these two sides of fixed shape and size, while this the height, the width itself is of variable. So the length is variable. We can then modify it or tune it with some mechanical saw down to our needs. Yeah, there are also some more common cases, like or dedicated cases for special applications, from plastic, from cast aluminum. Also, you can find cases with place for keyboard. Here is a place for some display with some diodes. Here is a place for a keyboard. So such cases are available as well. As also cases with panel, that we have the panel as a separate part, which means that we can use. They're quite convenient if you want to build a device with some LCD display, because then you can take out the panel and make a mechanical fixing to your display and PCB or buttons, for example. And those cases, to compare, they don't have a panel because they are constructed. They are like a C-tape box, mounting anything mechanical to those areas here isn't as simple, in fact, as in this kind of cases with dedicated panel. Here is a panel from aluminum. Very nice case with panel for aluminum for some device, yet horribly expensive to give you. This is from plastic. Take it. Well, this is about 100 euro per one case, so pricey, very pricey. As well, panels, you can find cases with panels made from different colored of plastic quite often. So like the red one, why the red one? This used to be used to mask the 7-segment LCD displays and the background behind those displays, because if you place a PCB with a 7-segment LCD, LED, sorry, of course, 7-segment LED displays, and then this colored plastic will hide the electronics and show only the displayed numbers. Yeah, various kinds of plastical element devices for smaller displays, larger displays, and so on. Yeah, we could go forever. Yeah, so something for remote controllers, for power supplies, they are dedicated. For DIN buses, the cases are here. Wall-mounted as well, desktop cases for sensors. So plenty of things, plenty of cases that we could choose from. Okay, that's fine. But what's the problem? The problem is that first of all, there are cases which are universal in size and shape, like for example, this case, this not really, this case, as well, the cases like those one, they are very universal, and you will find them anywhere, anytime. The problem is that if you design something to some dedicated case, like this one or this one, then after a few years you may, or this one, after a few years or even a few months, you can find that such a case, such a dedicated, special, very nice case is not delivered to the market anymore. And then you have to redesign your device and test it again, which costs a lot of money. It takes a lot of time. So that's problem number one. The cases, especially those dedicated ones, those very nice special cases, are quite often disappearing from the market. So this one, that you design something. Second problem, which should be even before mentioned before, the problem with cases missing from the market. And the second problem is that although there is a huge variety of the cases that you can, as I've shown you, but this number of cases, but they do require dedicated shape, for example, of a PCB board, or dedicated shape like you can see with this case, dedicated shape and size of the display. Which does mean that if you want to use such a case, if you are not afraid of this case disappearing from the market, then you have to take the case before or at the very early stage of your design process, and you have to adapt your PCB design and electric design sometimes to the case itself. Because, for example, you have to choose the display that fits into this window. And if the display is to fit into this window, it has to be mechanically fixed to this case, which means that the PCB as well has to be fixed to this case, which means that they have to be connected, I don't know, sometimes through some connectors, sometimes semi-flex PCB has to be used, and so on. So that's something you have to consider at quite an early stage of your design process. So that's the second disadvantage of those cases, which is, in my opinion, the worst. So you have to adapt your design to a ready predefined case. So if you have those two problems, how we can get around them? The idea number one is to design our own case. Today we have plenty of tools, cut tools on the market, 3D cut tools, and we have the printers. So we talked about this FDM technique, which is very cheap, which is very available, and yeah, so you have a computer, you install some, I don't know, maybe Fusion or some Autodesk Fusion or Autodesk Inventor or whatever CAD software you can get. Then you draw your case and you print it, and it's done. What's the advantage of this method with the use of the 3D printer and the dedicated case? The advantage is that you can then design the PCB, design the case much later in the design process, because you don't need to exactly shape it already during the PCB, between the schematic and the PCB design. You can do it after you have a PCB or during the time you wait for the PCB to be manufactured. And that's definitely the advantage. The second advantage is naturally the fact that the case will not disappear, because if you will have a project of the case, you can, if you're missing a case, then you will be able to print it again. Yet this has two serious disadvantages. Less important, in my opinion, disadvantage is the cost of the printout. The case here, this kind of a remote controller case, it costs a few euro usually. So those cases, the plastic one, are from few euros. While if you want to print it, it's gonna cost you more. Especially if you don't own the printer and you have to share, and you're sharing it with somebody, or you're hiring, even worse, from somebody, then the cost of the printout will be high. Disadvantage number two of this method are the materials. This is, in my opinion, way more serious problem than the cost itself, although cost is important. Because in those cases, for example, this is a remote controller, and we have a case where there is a plastic which is very nice in touch, which has a decent accuracy, but the second thing is that we have a second plastic, like this glass here, this transparent red plastic for the IRDA communication, for example. Or we have a situation like this one, that we have also heterogeneous case with different material for the shell and different material for the buttons. We can do it with printing, but we can change materials as well, because for example, with FDM, you can buy slightly different materials as your source for printer, as a source material. Still, you are not able to receive that kind of an accuracy and that kind of a touch you get from the ready cases, that you get from the ready cases. So don't forget about it. Besides the cases, the specialized cases, which we are sometimes interested in, like the cases for power supplies, you are not able to do it on the printer. Not yet, maybe in the future, but that's not obtainable in the future. And of course, the cases which are slightly better quality, like this one, which is aluminium based with some plastic as well, or the cases like this one, for example. Of course, you will not do them on the printer, and you will not unless you have a metal printer, but let's forget about it, because it's extremely expensive. So with the FDM printer, you can do simple cases, so you can avoid the use of this universal cases. So those cases you can really print better. You can do them better with the printer. But if you need the sturdy cases, if you need very good looking cases made with precision and quality, then you must live with those two problems mentioned for the universal cases. You have to live with the possibility that the case will disappear in the future, and with the necessity to analyze the case or to think about the case already between the schematic and the PCB design. So in this point in the design process. So that's where you need to think about it. Of course, there is a third path because printing is something you can do, but somebody might say, okay, I may order some machined case with the done on a standard with a standard technique of stamping or the technique of lathe and turning. Yes, I agree. That's the way number 3. So universal cases, printed cases, and the cases made in a traditional way. Yet don't forget, if you want to order cases of this kind or of this kind, done for you individual on the individual order, the cases will be horribly expensive. They will be horribly expensive. Horribly expensive because the machining, the classic machining, requires plenty of time, plenty of resources connected with the working on the materials, with the surface treatment of the elements of the case. Of course, the design has to be done on the case as well. So that the road number 3 with the cases, the choice number 3 is possible, but only if you work in a company that is having its own machine workshop and it's a custom and it has people familiar with design of cases for electronics and with the working on the cases themselves. In my opinion, the path number 3 should be the last choice. Should be the last choice in the in normal semi-professional and amateur for semi-professional and amateur electronics. Only for larger companies, that is the choice. Good. So we are done with the cases. The conclusion is that it's not simple. The conclusion is that you really usually must think about the cases before you proceed with PCB design and with PCB assembly and running. So you must really think about the cases before during your design process, and it's really not that simple. So I personally for me it's quite painful, the need to design the case to a design device, but maybe you will not find it as problematic as I do. Okay, next subject that the last on this circle, on this magic circle, are cables and connectors. So the last, yet of course not the least one, but it doesn't seem that important, but it doesn't seem that important. If it doesn't seem that important to you, the choice of cables and connectors, then you can try to take a look at your PC computer. Of course, here is a photo of the number of connectors on a bit older PC computer. Today, many of you have tablets, laptops with just a USB and maybe HDMI and the power supply. But even having just a few connectors means that there are a few different connectors that has to be chosen and adapted somehow. Of course, on the market there exist hundreds of various capabilities and first of all, need for connecting something to something. And during a design process as well, we need to think about it. So thinking about the case is one point of a problem, but then placing in the right part of the case a connector poses usually another serious issue, another serious problem that has to be considered. already during the PCB design phase, that cannot be usually left unattended until the very end of our design procedure, because the connectors themselves sometimes it can be seen here. Sometimes the connectors are very nice that you can mount them directly on the case, which is actually which is nice because you don't need to think very much about the electromechanical construction of your PCB and integration with the case. But many connectors like this one, this one, this one, this one, and this one, and this one, they all require special PCB supporting it. And the PCB then has to be integrated with the case in such a way that the connectors are visible and are available to the user. Of course, the number of connectors is, even if this seems even if I chose a picture with I don't know, there are 15 different connector types, but still, of course, it's far from the number that we can find on the market. I tried to make a classification of those connectors, but again, I don't think it's. I chose all the connector. I put here all the connector families then there exist on the market. Still, in my opinion, from practical point of view, those families are the largest ones. So what families do we have? So we have connectors for transmitting power. Of course, power connectors for electrical devices. So we don't talk about power connectors for kilowatts, but power connectors. Power here means that we want to supply our device with 1 watt, 2 watt, 5 watt, 50 watt maybe, but usually it's less. For electronic devices, normal ones, we need 2, 3, 4 watts, and the power connectors to deliver the good grounding and good power supply. We call them together power connectors. Then connectors for supplying audio signal. Also special connectors. They are a special family. Not a very high scale of integration in general, but quite reliable they have to be. Then various high frequency connectors like BNC, TNC, SMA, so various types of connectors. Some examples I will show you already after Christmas. D-tape connectors, so D-shape, D-tape connectors. So I will give you more about it. They seem old-fashioned and outdated, so these are this type of connectors. These are also the name of them is. But they are very mechanically decent outside. They are mechanically very decent, and still a good idea is to use them in a design, especially if you want to connect some cables to our device. Various edge tape connectors for integrating PCBs between themselves, or for connecting PCBs. Another way of connecting PCBs are the insulation displacement connectors, so-called IDCs. We'll talk about them again next time. Various pin header connectors as well, large category of connectors, very useful in practical realization because they are very universal, widespread and universal when doing connections for connecting, for example, some sensors, for interconnecting PCBs, for connecting keyboards, LCDs, and so on. So pin header will show those connectors, how they look like next time. And various temporary connectors, a huge family here of connectors of non-specified before. But there are really plenty of connectors of many types and sizes that we can cram into these temporary connectors. But again, we'll talk about it. We'll talk more about it next time we meet. Great. It's time now to say goodbye because it's almost a break. So thank you for your attention. This strange year, hopefully with all the vaccination going on, we'll be able to meet in practice, in physically, sometime next year, and that's my main wish for us for this Christmas and this new year. So keep healthy, that's the most important wish, and the second is the wish that we see each other not virtually but live at the university next year. Merry Christmas to you, Happy New Year, see you next time.